Hello, everyone. Thanks for joining us today. My name is Charles. I'm one of the presenters for today's webinar, along with Pete. Pete, would you like to say hello?
Hi, everyone.
Thanks. We're both application engineers for the Siemens SimCenter Test Lab product, and today's webinar is entitled SimCenter Test Lab Data Acquisition.
So this is where we get the true secrets to test lab data acquisition, Charles?
I hope you find some things you didn't know today. I don't know if these are true secrets.
Very curious. This will be good.
Okay. So the agenda for today is really just 5 items. I'm going to talk about channel setup tips, using channel setup tips specifically with signature acquisition. Talk about the CAN bus, how to set up that so we can measure some digital channels along with our data from our analog transducers. We're going to talk about virtual channel, coupling setting. What is that? What's the best one to use? And we're also going to talk about different methods of doing our test. We talk about tracking methods. And we actually have some information about setting triggers to help us with our data processing. The first topic we're going to get to is working with the channel setup. Show you some different things we can do when it comes to filling out our channel information to maybe eliminate errors that can come from typing in the wrong information or maybe the wrong channel direction. And I'm going to show you some tips if you work with a lot of Firex accelerometers. Why don't we move right over to the software? So when you open up signature acquisition, it'll probably open up here to the documentation page. And this is where you could document a lot of information related to your test. But today we're really going to just focus on the channel setup page, a little bit on the tracking, and we'll do some things on measure. So this is our channel setup page. Today I'm using a 1-slot Gaddis mobile front end. So I have 8 channels and 2 TACO channels. You can see I've turned on one of my TACO channels, and I have 1 dynamic channel turned on. And actually, I don't really have a test object. So what I'm doing is I have a recording of the RPM signal and the response from my accelerometer, recording on my computer, and I'm playing it out through the headphone jack into those 2 channels, the TACO channel as well as dynamic channel input 1.
But actually into a SCADIS as well.
Yeah.
Is that right?
Yeah.
Okay.
Yeah,
so you have
into the SCADIS mobile.
Okay.
Yeah. And I have a picture of it. We'll take a look at it later. So a lot of times, though, you don't just have 8 channels. Maybe you have like a V24. Maybe you have like 3 of those cards. So maybe you have 48, 72 channels. So instead of just maybe clicking to turn each one of these on, what you could do is just copy that, highlight it, and hit paste. That's one option. The other thing that you can do as well is instead of just doing copy and paste, you can do a drag down. We see all this says 0.1. For example, if I drag down, so I get the double arrow when I place my mouse near in there. I drag down, you'll see it'll kind of have an Excel-like feature. It actually increments by 1, 1, 2, 3, 4 now. Or if I wanted to, I could copy and I can do Control V. So a lot of the same functionalities that you see in maybe programs that you're familiar with, like Microsoft Excel, a lot of that functionality can work here for in the channel setup, which can be good to avoid forgetting to turn on certain channels, or in this case, maybe having to type in the same name over and over and maybe making a mistake. The other thing you can do is have lots
of double arrow to increments. Pretty cool. I like that one.
Yeah, that's a fan favorite.
And it won't let you have the same name for 2 different channels. Did I see that?
Well, you can't have the same. It will warn you. Let's say, for example, we've said channel 1 here. I'll make channel 1. We'll call it 0.1. We'll paste it in the next 2. If I have the same direction, plus X, then I get a warning. Duplicate point names found on channels. So that could be very helpful.
Confusing to have 2 channels with the exact same name. No, and I noticed it even grays out the measure. It's designed for people like me.
Yeah, we really try to help you out there. We don't want you to make any mistakes that you don't have to. Another thing is if you have a lot of channels, in this case, we'll just turn off half of them. We have that across the top. You can just say show on. So let's say if I have, a bigger front end with ability to have a lot more channels, I don't have to use all that space just to show all those empty channels. I'm not doing anything. So across the top here, we have show on channels or show on and off channels, whichever setup you desire. Another thing that's kind of cool with this channel setup, you probably don't have this channel, multi-channel, this display turned on. If you go to Tools at the top, Channel Setup Visibility. Do you see my channel visibility setup, Pete?
Yeah.
Okay. So this is all of the fields that we could turn on. By default, this multi-channel is not turned on, but you can turn it on by selecting it from the left-hand column here and just inserting it somewhere. We already have it turned on, so we don't really need to move it over. But what that's going to allow you to do is if you are working with Tri-X accelerometers, for example, let's do this. So fill this back down. So we see now it's just 0.1, 2, 3, 4, right? If I turn on, instead of going mono, go to Tri-X right hand, right? So I'm selecting Tri-X right hand because I want to use the right hand rule for defining the direction. So if I turn that on, you'll see automatically it decided that, oh, if you're using a Tri-X, then you have to have 3 channels. So it changed 0.2 to 0.1, 0.3.
The Tri-X is all at the same location, right? So it doesn't make sense to have different. And if you change any one of those, does it change them all at once? Type in Fred or
call
something.
It 11. Yeah.
Oh, sweet.
Yeah. So it tracks that for you. Additionally, which is probably the nicer feature, let me just go back to mono for a second. When we go to direction, you see you have a large number of options, right? X, Y, Z, the positive and negative. We have some rotation. We have a scalar for S. When you are using Tri-X and we want to basically maintain the right-hand rule for setting our direction on our channel, you'll see automatically your list is more restricted. We don't have scalar. We don't have the rotation. We just have X, Y, and Z. So let's say we say this is negative X. When I go to the following channel, I no longer have X as an option, right? Because I've already selected it. So I have to choose one of the Y or Z directions, and depending on how my Excel is oriented, it actually selects Z for me. I have no other option because based on the right-hand rule, if I have negative X and positive Y, then the other channel has to be in the negative Z direction according to the right-hand rule. So that's really helpful so that you don't have any animations for your mold shapes or your ODS measurements that are incorrect because of a mistake made in setting a direction.
Hey, Charles, we have a little more, I guess I'd call it basic of a question.
Mm-hmm.
They're wondering, can we use a name other than 0.1, 2, 3?
Yeah, I know you're partial to Fred.
Yeah, so Fred, but there's really even I think it's a pretty generous amount of characters. How many can you keep typing in there? See how, you can call this anything you want, right?
Yeah.
Fred.
Yeah, a lot of options. Right?
So it could be pretty descriptive, huh?
Yes, very. The other thing I wanted to show here quickly was the idea that this channel setup is per section. So if we have a different section, we can have a totally different setup. So this is section 1 that we're working in right now, but I actually have a lot more sections in this project. And you can load another section. For example, let's say I have a different section that has a different setup of accelerometers and names, and I want to use that for my test. I can load it from another project, maybe that I've already measured in the past. I can do that. Or from the active project, I can choose one of my sections. I can say maybe section 3. And I can say, well, before I load that in, what does it look like? So I can say view setup. And I say, that's not the one I wanted. Let me look at section 2. View that setup. Like, okay, yeah, this is what I got. A couple microphones here at the bottom. I had several accelerometers. You can see the sensitivity. So all of the channel setup information available, all those fields, whether they're displayed or not, that can be loaded. Or if you want to just basically load some of the information, maybe just a channel identification or tackle information, whatever, you can do the complete setup or a portion of it. The other thing is, why don't we just load that one, for example? So you can see it changed everything for us, right? Turned on all these other channels, defined the direction, they were ICP, sensitivity. Another thing, you may work with different front ends. If that's the case, maybe we hope you have, a lot of our hardware, and you have some different configurations of cards. If that's the case, what you can do is choose skip inconsistent channels sometimes, this may be an option you want to turn on because you may be working with a front end that has cards that maybe your original test didn't have. So for example, maybe you have a V8 card and you did the first test and you just have voltage AC, voltage DC, and ICP as your input mode. Whereas you now are working with a system that has like a VBA card, which has a lot more options. We're actually going to talk about that later. So like drain and potentiometers, a bunch of things. So when you go to load your setup, you may need to turn this on so that it understands if I don't have those channels to skip it. If I don't have the ability to use a strain gauge because I don't have that card. So that's a handy option. But nevertheless, you should always check after you do a load configuration. You should always check. Another way to load a configuration, for example, is actually some test data. Let's look at some data. So if we go to the Navigator tab and we go to Run, we actually have just Archive Settings. And if you right-click on Archive Settings, you actually have a couple options maybe you've never known about. You can view the channel setup that was used to do that measurement. I can also load it if I want to into my channel setup to redo a test. Or I could do View Archive Settings. And this is not just the channel setup, but all of the data acquisition settings to measure the data. So this is like nearly 600 parameters here. So you could view all those if there was questions about the setup, or you could actually load all of the archive settings as well. Going back to channel setup, those were some of the things I wanted to show you with regard to this particular tab and maybe working with it to make setting up the test a little bit more efficiently. Okay, let's go back to PowerPoint. So we're going to talk about the CAN bus now for a few minutes, setting that up. Now, a couple of things you need to do before you can even start to set up your CAN bus to measure information for you. You need to go to add-ins and turn on this add-in called Vehicle Bus, and that's 22 tokens. That needs to be turned on. And then you can, from there, go to channel setup and select CAN settings, and then you're going to get to a page like this. And let's see what that looks like in the software. So just reiterated tools, add-ins, Vehicle Bus, I already have it turned on. Go to channel setup and go to CAN settings. From here, there's a couple things you need to do. First, select a CAN device. Most of the time, unless you have what we call a CN4 card, you're going to select this XI1, which is basically the CAN on your control card, your Syscon control card on your front end. You select that. The baud rate, there are different baud rates. That could be 125,000, 250,000. The default right now is set for 500,000, which from an automotive background, that's all I've ever really used and had much success with using that as the baud rate for communication. But it is adjustable, so if you need to change it, you can. But if you're working on a vehicle, I would say that's probably going to be what it is, and that's a good starting point. Next thing we need to do is select our DBC file. I'm just going to select this basic one. It's not really a very complete one. It's just for an example. But you select this path to wherever you have that DBC file. And that DBC file, if you haven't really used a lot of CAN DBC files, is really just a list of all of the electronic control units with the ECU. It's an ASCII file, basically. It's a list of like all the inputs and output signals that are broadcast on that CAN network, which stands for Controller Area Network. That's the acronym stands for. And it has all those signal names, scale factors, offset, default values. Basically, you need this information to read that CAN signal, to decode it into something meaningful for you to have in your result. So once you turn on your device, set your baud rate, browse to the path of your DBC file, make sure you have clicked on View CAN and Overview. One other thing with CAN, you can set it to passive. If you're using a DBC file, for example, we provide in the test lab install a DBC file that allows you to read channels that are associated with emissions testing. Those aren't broadcast normally, so you have to use active. But in most cases with normal CAN, you're going to be reading data that's already broadcast, so you don't need to choose active. But active is basically telling it to request the information. So request the information and then records it and keeps going back and forth. Passive is typical setting though. So you want to hit show all. We have this filter on. Let's turn that off. Show all. And then typically this is a lot bigger file for most scan. Standard file would be like, I don't know, 1,000, 1,400. It could be more, depending how many electronic control units are in the vehicle. And these are probably growing exponentially with electric cars. So that might even be on the low side, saying 1,000 or 1,400. So as these lists get really long, it's difficult to search through them. Like you can turn off certain parts of it, depending how it's organized. But even better is if you know what you're looking for. So if, let's say, I'm interested in gear, all right, it's obviously not an electric car, maybe. You can just filter by gear. And I'm like, okay, I can find what I'm looking for and select that. Or maybe, I'm looking for something else like RPM. Okay, this is what I'm looking for. Selected it. And once you hit apply, now when we go back to CAN settings, we'll be able to see it in our channel list. So we go back to channel setup and we can see what we turned on. We selected the RPM signal, right? The engine speed. One thing I want to show you here, this digital bus under digital bus channels is raw data. If you turn this on, what this is basically doing is saving the entire CAN stream. So where this can be useful is if you don't have a DBC file or you have a DBC file that isn't very complete, you have some other channels that you would like to have, but you don't have any of the output signal information, scale factors, offset, so you really can't read it. If you turn this on, it's going to save that entire CAN stream, and later on, we can decode it and use that information. So that's a useful thing if you're doing the test and you don't have a DBC file right then, but you still want that information. You can turn this on and it saves the raw file, and we can browse it later.
So the channels you selected before were just for visualizing online, but at the same time, in addition to the ones that we see live, we can record them all in the background. Is that kind of what that's doing?
Exactly. And we actually have a demo here. Let's look at this video. So this is showing us where we kind of left off. We selected the RPM, applied it, just showing you that I am saving the raw data. Instead of having that long name that maybe is a little bit overcomplicated, we can change that point ID to something more simple but still meaningful. Call it CAN engine RPM. And once we're set here, we can go to measure. And from here, we can go to our data explorer. And if I want to have a display of the numerical values, so I can kind of have a heads up display of the values. And also I can look at the time history of the RPM as my test is running. So now I'm going to arm it.
Now, turn on my car. And you can see the engine RPM updating. And as I press the gas,
you guys are hearing anything.
You can see the RPM changes.
Basically, it should have showed the car starting and showing throttle blip.
And that is how you record CAN channels
as we
plus analog channels,
so
all
you can
in
see
one
how
acquisition.
easily it is to
Thank you.
use these CAN channels, track RPM. So we're going to talk about virtual channels now. To show our virtual channel setups, once again, we go to the same spot on the channel setup worksheet. We go over to the menu, drop down, grab virtual channels, and you're going to get a setup like this. And before we go to the software, just highlight a couple things. One is that this virtual channels that we're creating here, we'll be able to visualize this data online while we're testing. And of course, offline, it'll be stored with the rest of our channels from our other transducers that we have connected to our front end. So let's take a look at that in software. And let's go over here to channel setup, like we showed. Go down to virtual channel. And what these virtual channels allow us to do is, we don't have very many channels turned on here, but what we can do some basic math on them. So I'm just taking CH1, that's my channel input 1, multiplying by 2. I mean, it could do anything. It could do other math operations such as subtraction, division, whatever. There's actually even more complex functions we can perform. So if we click on the next line here and we go to insert a function, you can see a list. If you can filter these two, but depending on what you're looking for. But if you go to all to kind of give you an overview of all the functions that we can do on this time data right here. Some related to the TACO as well, this PWM if you're messing with some pulse width modulation stuff, filtering, All these are possible. And that's basically what I did here. I turned on the filter, and we're just going to use the low pass filter on channel 1, 500 hertz cutoff frequency. The default name will be like virtual 1, virtual 2. You can give it a point ID to something more meaningful. You can give it a direction. You can change what group it's going to be in. Keep it in a vibration, but it can be acoustic, other, static, whatever we want. And let's go down here to measure, just to show you that you can watch this data live. So if we go to ARM, and I just created a display, and I dropped in from my online data manager all of the data from the monitoring folder here from the time history. I just dropped that in there. So that,
Yeah, so the green one is filtered, so it looks like it's less in amplitude than the other ones because it's being
right, exactly.
Cool.
So, and we haven't even started the measurement, right? This is just in ARM mode, right? We're monitoring those signals before we even start the measurement. And that'll include our transducer data as well as the virtual channels we created. Additionally, if you were doing some structural functions, you can also look at that data as well, live.
So if you looked at
the
that
virtual
at
channel.
dB or something, that green one would probably not have much frequency content compared to the others, huh?
Yeah.
Yeah, been filtered the heck out of it as they.
Exactly. So that was the demo that I wanted to show there with regard to the virtual channels. And really quickly, just over, if we were to run our test, right, here's an example of a run. If I go to the throughput to time data, you can see it saved right alongside my analog data, the data from my analog transducers. I have to say, we digitized it to get it into test lab. But it's right there. It's accessible very easily. Go ahead, Pete. What do you want to do?
Yeah, if you go back to channel setup, I noticed you were using the channel number to refer to channels, but let's say the point ID of the first one was Fred. Can we type that in the actual, you know how much I like the Fred ID. So now
Yeah.
down here, yeah, can we say Fred and it'll still work?
Yeah, we can.
Oh, there's a direction on it. You have to say none for the direction, I think. You have a direction up top?
Yeah, let's do that. There we go.
So yeah, that's nice. If you don't know what channel something's going to be on, but you know the name, you can set up those virtual channels to use the name rather than the channel number on.
That's very handy, yeah. That would give you a lot more flexibility and avoid a lot of mistakes sometimes that can happen. Okay, go back to the PowerPoint. We're going to talk about coupling settings. Another thing on the channel setup that you'll probably notice is this input mode. And the question might be, well, what do I set that to? If you have, we talked about earlier, like you can have different cards. If you have like a V8, you're probably just going to see these, not probably, you'll just see these voltage AC, voltage DC, and ICP. Have a little fancier card, like a VB8, for example, or something similar. You're going to see a lot of other options. Most of these are associated, obviously, with strain gauge for bridge completion, linear variable displacement transducer, potentiometer. So you have a lot of other options. But today we're going to keep it simple, and we'll just focus on this idea of what input mode should I choose. Do I want AC coupling, DC coupling, or ICP? First question, I guess, is what is coupling? We don't want to overthink it, but coupling is just the electrical connection between our transducer and our front end. We have the definition here. Coupling is a transfer of electrical energy between two mediums by means of a physical contact. So this is the setup I actually have right here on the desk in front of me. This one slot, and I actually have one RPM, and I'm using one dynamic channel, right? So it's be two coupling. So the question then is, okay, should I AC couple my signal or should I DC couple my signal? You know, what does that mean? Well, what's meant by AC and DC coupling? Well, most signals are composed of both AC and DC components. The DC component would be the components that show the offset from zero or this mean value, while the AC shows this fluctuation of the signal. So if we look at it in the frequency spectrum, that DC is going to show up at 0 hertz, that offset and mean value. And the AC will be the fluctuation that will be at all of the non-zero frequency information in our signal. So when we look at the med signal, we'll have an AC and a DC portion, one representing the fluctuation, the other representing the offset. And this is how it kind of shows up as we see in our frequency spectrum. I have a video here starring Pete and our friend Thomas that we're going to play next. And they'll go into a little bit more detail. Just wanted to give you a primer so you know what they're talking about.
Today we're going to talk about AC and DC coupling. And we got a signal that we're going to try and measure here. What type of signal is this, Tom?
This is a AC signal.
It's AC because it's fluctuating around, right?
Yep, fluctuating around down the zero.
We have this hooked up to a signal generator, right? Mm-hmm. And if we wanted to see a DC component on this signal, what would you do there?
All we have to do is go to the DC offset dial on our signal generator and move it.
Ooh, look at that. It's like rising up. Wow. So you've added a DC offset onto this signal. It's no longer centered around zero. And in fact, I can right click here and I can put on a double Y cursor and we could kind of get an idea of how much that DC offset is. Looks like it's about 0.6 or maybe a little less volts or so. So you added a DC offset. So this signal really has two components, an offset plus the AC. Can we even do something on the AC? Like
yes,
you
we can.
Change...
I can change the amplitude right here, and it'll change the amount that the signal fluctuates.
Oh, okay, so you could even eliminate that. Now, when we go to measure the signal, there's a coupling field on the channel, and that can tell us whether we can see the DC or the AC component. I'll go to channel setup here, and we can see that, in fact, we have this signal. Is it teed into our system?
Yes, it is.
So we got a splitter coming out of the signal generator, and it's going into two different channels on our front end. And they're both were set to DC coupled, but I'm going to switch one of these to AC coupling. So we got the same signal coming in, and it has both an AC and a DC portion, and one is going to be AC coupled and one's going to be DC coupled. Let's see what happens to our signal. So, wow. So we got one of the signals with the DC coupling still sees the DC offset and the fluctuating component, the AC, right? And then what happened to the green one, Tom?
So the green one's only measuring AC, so it doesn't measure the offset, which is the DC component of it. It only measures the amplitude.
So there's actually an offset on the green channel, but we can't see it because we set the mode to AC coupled.
Correct.
Huh, interesting. I guess this might apply to accelerometers. When I measure an accelerometer, sometimes I measure the vibration of things. Well, let's see. You got an accelerometer hooked up here?
Yes, we do, right here.
Okay.
This is what's called a DC accelerometer.
So we have a DC accelerometer hooked up, and right now it looks like it's measuring about 1 G. Why is it measuring 1 G? It's not even moving.
It's measuring the gravity.
Oh, yeah. So what happens if you flip that upside down?
So if I flip it, you can see that it flips it to -1.
Oh. So now instead of things floating down, now they would float up or something.
Yeah, sounds right.
Okay. We're able to measure the DC offset, and I saw as you were like kind of pounding there that we could see the AC stuff too.
Yeah.
Yeah, so we could see both the AC and the DC. If I go and look at the channel setup, it's set to voltage DC. Let's flip it to voltage AC and see what happens. Now when I go to measure, am I going to see that gravity offset?
You will not.
Let's see what it reads. Wow, we've eliminated gravity. Cool. But we can still see AC vibration?
Yes, we can.
Cool. AC coupling gets rid of any kind of DC offset. But if you have DC coupling, you can actually see both an AC and DC portion
Correct.
of the signal. Cool.
Great. Let me switch back to our presentation. So hopefully you all enjoyed that demo. I thought they did a really great job explaining AC and DC coupling. And now maybe you feel like you got a good handle on this. We can talk about a few other things. So what kind of coupling should I use for my transducers? Well, a little bit depends on what you're trying to accomplish, what type of transducer it is. For ICP microphones and accelerometers, we should have those AC coupled. And here's an interesting point. Maybe you use the term ICP, maybe you use the term IEPE, or maybe CCLD. They all mean the same thing. Those all need to be AC coupled. And actually, the voltage supply to those ICP transducers to power them is actually at that 0 hertz. And we remove that by AC coupling them. So on the front end, on the input mode, if you have an ICP accelerometer or microphone, for example, you need to select ICP. It is AC coupled, but you need to select ICP because then we're telling the front end to send power to that transducer so that it works. Strain gauges can be AC coupled. Going down to DC coupling, that could be for thermocouples, maybe. We would use DC, or obviously for a DC accelerometer, kind of as the name implies. We would DC couple that because we're interested in the effects of gravity, that offset is caused by that. Or we could actually DC couple our strain gauges when we're interested in things, the mean value, the offset, kind of where plastic deformation is the key thing we're looking at. Last thing we're going to talk about on the tracking setup page, there is a lot of important information you need to look at and set. So we're only going to talk about 2 things, detailed information. But really today, I only want to talk about the tracking method. That's the major choice we need to make when we're on this tracking setup page. Are we going to do tracked or stationary? Because we get quite different results. Tracked, we get this waterfall, or it could be a color map plot, a lot of different spectral measurements at different RPM or time steps. Or stationary, we get one average FST. Now let's go to the software to take a look at that. Go to stationary, and we'll go to the tracking page. And see, well, maybe I want to move this up just a tad. We can see we've already set the tracking mode to stationary, and we're going to just do time tracks. You could do free run or some event. We'll just do time, and we're going to make this shorter. Let's do 20 seconds or something. And we're going to do 2 averages per second. So let's go to our measure tab, and we're going to arm it, and we'll hit start. And we're just going to go. We're going to take all 41 of our averages, and you can see each one as it's updating, as it's going. But this is good for if you're measuring something that's maybe at a constant speed, it's not changing very much, then you would want to use stationary because you're just interested in maybe the frequency content and amplitude. So when we save that and go to our navigator, so run 3, stationary, and we go to the results into the stationary folder, we just have one FF2, right? In the window, just dropping it. That's the average result from all 41 of our measurements, our averages. So if we go to tracking setup, again, in this time, we go to tracked, and let's say we track on our TACO RPM, right? We'll just do 1200 to 3800 with a step of 25 RPM in between each one. If we go to measure here, so I'll go to track so we get the right displays. I created some displays already for us. And go to measure, earn it. And let's see where we're at. We're going up. So it's set to the slope is up. So it's looking for an up slope from 1200 going forward. So in our RPM, my recording is actually at the high end right
So
now.
it won't take data till it crosses 1200 RPM?
In the correct direction. Yeah. So now that it's down, we'll start. And it's waiting now to get back to that start point, 1200 RPM. Starts measuring. We're using a color map or Campbell plot here.
Which is tracked.
Yes.
All right.
So just really quickly, and now we will stop it and go to our result. We will throw a color map up here, I suppose, and we will go to tracked and look at this. So now when we go to inside the fixed sample, we have a run up folder, and inside of it we have a measurement at each RPM step. We had those 25 RPM increment steps. So each RPM increment, it grabs a chunk of data, calculates an FFT. So if I grab all of those and put it here, and maybe let's make this dB so it looks a little more exciting, and zoom in a bit, we can see a few things. We can see some orders, right? I could put an order cursor here. So what is this? Third order, some 6, some stuff at 12. I see some structural resonances, that 12th order. Exciting, helping to excite that structural resonance right here at this frequency. So that's the major difference when we talk about the channel setup for tracking. If you want to measure something, if it's important to see how your structure, your vehicle responds as you're sweeping through an RPM or a speed or its time changing dynamically a lot, you want to do tracked. You can do tracked on time, you can do tracked on RPM or speed. Or if it's more of a stationary measurement, a single speed, that would be more appropriate to use the stationary for track. And while we're on the subject of tracking, let's go back to our PowerPoint. When we talk about signature acquisition, there's 2 different places that you can set some triggers, and that's important for tracking. So on the tracking setup tab, what we were just on, you can set trigger information here. Also on the acquisition setup page, there's the ability to set triggers. The important thing to know is that they don't do the same thing. They're both called trigger settings, but how they work is a little bit different. This one triggers once during the measurement. So you might have like some start condition. You're waiting for, a temperature, or you might have a microphone. You're waiting for some sound pressure level to be achieved. Then it starts the tracking. It'll look for the 1200 RPM and the right slope, and it'll go to that RPM maximum and stop. If you are using trigger settings on acquisition setup, that's on a block by block basis. So each chunk of data requires a trigger before it goes to the next block and grabs that data, calculates the FFT, and saves it. So be careful. There are instances where you want to do this on a block by block basis, perhaps. And then there's times when you just really need one trigger signal, and this is where you would want to set it. And we actually have another video, Pete starring in, that highlights a little bit more about triggering. I'm going to play that for you right now.
I'm going to talk about using triggers to capture transient events in LMS Test Lab Signature. I have set up here a single acoustic microphone, and it's hooked up to my Scatus XS. Under tracking setup here, I've set my tracking duration for my acquisition to 3 seconds because it's a very short event. I don't need to capture data for very long. And now I'm going to go to measure, and I'm going to show without triggers some of the challenges of measuring transient events. Under Data Explorer here, I can set up a channel, the microphone in particular, to monitor while I'm taking data. So I'm grabbing under the time history folder, the microphone. And even though I'm capturing 3 seconds, might be useful to see a little bit more time. So under the More button, I've set the time history size to 20 seconds. And now when I arm, I can see the microphone recording here. If I have a transient event like the snapping of my fingers, that also shows up. And now I'll try and capture that snapping of my fingers. So here I have to know, okay, the transient's going to occur, so I hit start. Transient occurs, and hopefully I capture it in 3 seconds. And then I'm going to go and get ready to measure the next transient. So I hit start again. Transient occurs, and hopefully I got that. And now maybe my next transient's occurring already, and I have this thing asking me if I want to keep this run. So one of the things I could do to be a little more efficient here is under More here I could say, look, automatically accept the measurement, don't prompt me. So now when I hit arm and start, I can capture the next transient, and it's not going to ask me. It's just ready to do the next one. So I've captured 4 transients here, and I can go and look at those in the navigator And if I take a look at the first recording here, got my transient. I can look at the second recording. There's my transient, my next one, and my next one. And you can see that these transient events occur all at different points during the measurement. They're not all aligned in time, which could make it hard to analyze and understand what's going on. So what I'd like to do is trigger this so that I get a consistent place where this event occurs so I can overlay and compare these. So I'm going to go to the tracking setup here. I'm going to turn on triggered start, and under more here I can say, hey, when the level hits 2 pascals, that's when you should start recording. And I can also create a throughput pre-start, and in this case I'm making it 3 seconds, and what that'll do is capture 3 seconds leading up to the transient event, to that level. So now I'll go to measure, and the behavior will be a little bit different now. I'll hit arm, and notice it takes 3 extra seconds to arm because it's buffered 3 seconds worth of data. I hit start to measure, but it doesn't start measuring right away. Now it's waiting for a trigger, and it didn't acquire till I snapped my fingers. And now it's automatically getting ready for the next measurement. I'll hit start, and now captured that, and maybe I'll do one more for fun. Had to have a sufficiently high transient. And now we can take a look at these events and see how they compare in the navigator. So I go over there, I'm going to remove these previous curves, and we'll go to the next 3 runs. So we had 4 of them. Now I'm going to run 5, run 6, and run 7. And notice, if I was to zoom in here, all of these events are all aligned well in time, making comparison of their levels a lot easier in the time domain. So now I'll go back to the measure screen here, and I'll show another feature. So when we're measuring, we might want to capture several transients. We want them all aligned in time at 3 seconds. We can say under here, measurement sequence, we can say, for example, if I want 4 runs, I'll say 4, and it will automatically rearm and capture 4 runs in a row. And if I want to minimize the time before it can capture the next event, I can also come up here and say delayed processing. By delaying processing, no FFTs or anything else will be captured. All that happens is it tries to record raw time data. So we're ready for start. Notice it has run 1 of 4 up here, so I'm going to hit start here. Nothing's happening till I trigger. And now we have measurement 1 of 4, and we're ready for 2 of 4. It's going. And it's keeping track of how many measurements I've done. 3 of 4. And now 4 of 4. And so I didn't have to use the mouse, the keyboard. I didn't have to worry about missing the event. Everything triggered automatically to capture. Now I can take a look at the transient events. So if I look at the last 4 runs here, we can verify that the transient did occur at the same spot in all 4, and makes it easy to overlay.
Hopefully you all enjoyed that video. I think it was very well done, Pete. Thanks a lot for that. If you have any other questions about this subject, the signature data acquisition, have a great day.
Thanks, Charles.